Thank you. Just a little bit about myself. I think many of you know me anyway, so I'm pretty active in the Python community and chairing 3 conferences this year. I did not plan for the 3rd one. This guy made me do it. Okay, so yeah, I just founded PyData Frankfurt and PyData Southwest in Germany. So if you ever change flights in Frankfurt, let me know. We may arrange a meetup and you can give a talk. So I like to talk and speak and train, and a little bit more what we do as a company. We are a small consultancy, or like middle-sized consultancy. So we are basically focused on consulting on digital innovation, and we do that in the enterprise space and in the finance space, and also with startups. But fair enough about myself. What about you? Because like this is a little special topic. Or like my usual. So I would like to know a little bit more about what's your background. So who's a data scientist? Okay, that's right what I expected. And then who's more like a database admin? Okay, welcome, you 3. And who's more like a curious Pythonista? Okay, okay. So, and who's a consultant, IT executive, or YouTube influencer? Okay. So, okay, that's basically what I expected, because I adapted this talk last 2 weeks ago. I spoke at the MongoDB conference, and it was mostly more admins than data scientists. So here we have more data scientists. So I need to know more about you as a data scientist, especially, or everyone. What's your expertise in relational databases in general? Just like, who knows? Okay, relational databases create. So who? Okay. So, and in the whole no SQL, not only SQL space. Okay. And who's more like into stuff like Hadoop? Okay. Okay. So, and last but not least, what are you looking for? Is it more like integration into something you know which could help you on your data science project? Okay, yeah. So learning about data science in general for data science projects? Okay, cool. So, general interest, and last, who's just killing time until Pi Frontier? Oh, okay. At least you're honest. Yeah, at least you're honest. So, okay. Basically, for me, there are 3 angles for choosing a database for a data science project. It's let me just increase. Okay, I can read this better here. There's choosing a database for a data science project. So the question is, how can a database help you on data science projects? Because data science projects tend to depend many times on files. The other thing is evaluating an existing database for data science requirements. So if you come to a company, you cannot say, hey, Alex Hendorf told me to use this great database, and please change your ecosystem if you join a company. And also, of course, how to integrate into an existing ecosystem. So how did I ever come to the idea of this talk? Actually, it started last year because I received a message from Emmanuelle, and she's chair of the Euroside Pi conference coming to Italy this year, to Trento in August. And she asked me, hey, can you provide like an SQL training? I think there's a gap in our scientists and data scientists community. And actually, I had to deny because I was at a client all week. So, but it really got me thinking. So for me, because I come from a database application development background and moved to data science, so for me, if I ever had any trouble with a data science project, or if I felt a database could help me in my research or like data science project, of course I just took a database and so. But thinking about it, okay, all the tutorials I see, it's all file-based, or big guns with Hadoop, or Spark. And so how deeply does data science and database understand each other? Like, is there like a gap, and what can I provide to close this gap? So, so if I'm not sure, I usually ask Google. So data scientist, database admin, what is the Google search stereotype? So this is the Google search stereotype for the data scientist. So we see people looking smart, glasses, and some women, and but you know, like this weird scientist looking or superhero. No, okay. Let's move to the database admin. That's usually be guys running the databases. So, and here this is like also like super cliche. They all have these server racks and look like here and plan and stuff. So, so looks like it works like this from the database science background. Okay, you read it through. So basically, this talk is based on research and my personal experience from myself, colleagues, friends, acquaintances, and it's supposed to give you a guideline. So for the data science perspective for choosing a database. So because we seem there's a gap, and let's close that. So also some of these ratings are subjective. You will see some ratings that are subjective, but the ratings as such do not matter probably that much because it's more like the method we're talking about. Let's go. So what are the benefits of a database for data science anyway? It's a common source of data. You can avoid redundancies, for example, like having multiple copies of the same file and going through network drives, exchange with colleagues, and asking yourself what's the most recent version, especially which one is the one with the clean data set. We have persistence, and also databases are around for decades. So of course they are also like optimized for data aggregation. And one point is really data aggregation, very, very close to the data. Not only we have a database, the database can access data really fast, and of course this has been optimized for decades. We have scalability, possibility of scalability with databases, and yeah. And so, just like a quick recap, where come databases from? Like in the 60s, we had like navigational databases, disks and drums. This is the stuff you see in science fiction movies with like these huge things and like these rotating things, and the times where people said, "Oh, there's only like a market for 5 computers worldwide." It was, by the way, the boss of IBM who said that. So in the 70s, the idea or the concept of relational databases came up. In the 1980s, the databases moved to the personal computer's desktop. In 1990, we got the concept of object-oriented databases, and in the 2000s, the whole NoSQL movement started, because relational databases were, for many use cases, just not good enough or sufficient for reasons I'm going to explain in a bit. So this is so relational databases. Their records, those you don't know, records are organized in tables. It's like a whole bunch of Google Sheets or Excel sheets. The rows of these tables are identified by unique keys, and the whole tables are basically all connected with these keys. And the data spans across all these multiple tables, just sharing the links, so the data is highly normalized. Of course, there's also like the denormalization, but I have to generalize a little bit in the talk to get the message across. And transactions are assets, so they're atomic, consistent, isolated, and durable. So it's basically you put something in a database and it's guaranteed this is the truth and nothing but the truth. Of course, during the years, there's are many. This is just like the relational database systems and basically how they the generology of them. So you see, there's a lot of them, and there's been like they're all partly interconnected. So it looks like this. So yeah. So the relational database benefits are they're widely used and supported, and they're around for decades. So, and they normalize data, which is looks like this is a good thing. Normalized data, we only have the data once. There's a very comprehensive querying language, SQL querying language, with some differences between the databases, but it is it's a good standard. It's well researched and taken. So actually, I talked about tables and these interlinks, and this is like the relational model looks like. Nice. Read all that. If you have a bigger system, it looks like maybe like this. And who knows about relational databases already can guess the next slide, because if it's a bigger system, it can look like this, and it's really hard to keep track. So what are the downsides of relational databases? So how did people think, oh, let's build different systems, let's rethink databases? The schema is defined. So this is basically a database schema. We have these columns and values and tables interconnected. This is our schema. So basically, it's schema first. So you have to decide, this is the schema, you have to program it, and then you can put in data. Altering a schema is not trivial, because like if you have a huge system, it can be really hard because other stuff depends on it. And this is also the solution why maybe database admins are not like the most favorite people in the in companies, because they have to be very defensive. They have to protect the systems as well. Joining tables depending on the complexity, because if we want to pull more data out, we have to join the tables, we have to join the information together again, and depending on the complexity of the systems and the amount of joins we need, this can also be like quite complex and costly. And of course, since everything's very distributed, it's difficult to scale. And we basically only have few data structures. We only have tables and rows. So what's basically the approach of the NoSQL movement which came up? In NoSQL, we have four main types. So there's a key value store. This is the very simplest form of a NoSQL database. So basically, we just have a key and a value. It's just like an ID and one value. So, okay, so I think this is not very useful for us because we usually have some more values at hand. Then there's the document databases. They usually save like a whole document in JSON style. They have an open schema. So you don't need to predefine anything up front before you can add data to the database. So it's super cool to add data from outside sources. Then there's the white column databases. They look from the outside a little bit relational databases, but the schema is also not fixed, and it's the data is denormalized, but the handling is very different. And there's the graph databases, handling graphs. So let's see what are the benefits of these systems. There's no need to normalize data, so we have no schema enforcement. This is also one big misunderstanding. Of course, you can control the schema, you can enforce the schema, but by design you don't have to. So you can plug in any data source and just like pull in the data and look at it later and deal with it. You can maintain complex data structures, as we will see later. So you can have like an array of subdocuments. So you don't have to tear, for example, multidimensional data. You don't have to tear it apart in a NoSQL system. There's new ways to query, and also like since we have documents or like other data structures, they are much more easy to distribute and to replicate. What are the downsides? One thing, and also like often misunderstood depending on the also like local language, is eventual consistency. Because for example, eventual hierarchy means like, okay, maybe, yeah, but this is wrong. Eventual consistency says distributing the data will take some time, and until the systems communicate with each other and have basically the same set of data, it may take some time, but eventually they will be consistent. So it's just like a matter of time and communication. And usually in a healthy system, this goes like really fast in a matter of milliseconds. The flexibility requires more responsibility. So I'm allowed to put all the data and stuff in there. So responsibility moves from schema definition to my program. So if I want to really check to put integers in that attribute, I should do that before I add it to the database probably. So a quick bird's eye view. Where do we stand with these both systems? So I looked at DBEngines ranking.com, And this is like the development of the multiple systems, and I highlighted only the top 10 systems according to these DB rankings. And this is just like one approach, you know this, which is the best language. And there's still some other rankings we claim it's not Python but Java, but well, you know these sites. So this is based, but we see like a trend. We have like these SQL systems, and we have these new systems basically coming here. And I did a little other approach because the site also assigns points for database systems. So I created a different view. So on the left-hand side, we see the NoSQL systems according to the points. The points say this is the importance of the system in the general market. And we see the relational database system. And one thing is very obvious. We have Oracle, and MySQL is in a way it's also open source, but it belongs to Oracle, and there's also non-open source versions. We have Microsoft SQL Server, and then the first open source project here, the real one, 100%, is PostgreSQL. So we see relational databases are very dominated by proprietary software, while we see it's also like the whole database market is still very much dominated by relational database systems, and this is, of course, big enterprises run these systems, and if you have a big enterprise, you cannot just exchange databases because there's a new hype or a new thing. So they will stay there for a while. On the other, we see on the NoSQL movement, we see like MongoDB, Elasticsearch not being a database, and Cassandra, for example, here. And this is only, also have to say, this is like only 10 years time. So this is also already a huge market share because like big companies move slowly, not all startups. So there are two consistency models of these databases, which basically, so there's one asset, atomicity, consistency, isolation, durability. So if you send something to the database, it will not affect any other requests or inserts to the database. It will be stored, it's like super guaranteed. And since for the NoSQL systems, there's base, and base, as you see, is a little made up. It had to fit to ACID. So we have basic availability. So we have soft state and eventual consistency. And basically, I would not worry too much about it, especially in a data science context, because these are things you have to really worry about if you run a production system, if you run a web shop, if customers buy stuff and you have to store it in databases. So if you do analytics on a system, and I would argue we hardly do like live analytics, and it depends on the last seconds of data we have in our system, we don't have to worry about this at all. So I did an open source check because there's very good reasons nowadays or forever like to work with open source software. Security, transparency, it's engaging collaboration, quality, audibility. I mean, I think you all aware we work with an open source language, and we are very happy with that. And also a rule of thumb, open source software system is, even if there's like an enterprise version or like a professional version or a version with support, it's much more affordable than the closed systems. So I hear many people complaining about like, oh, I have an Oracle database and it's very expensive. And it's all. Okay, so I've chosen the following contenders. I've excluded the proprietary systems because we're talking about open source, and I thought this is like the top representatives of databases being available in an open source software license. So there's PostgreSQL, which is for relational database systems, MongoDB as a document store, Cassandra as a white column store, and Neo4j for graph databases. And just to you see a little bit more, like this is again like the relational database system with the tables, and this is what we call a database. In a document-oriented databases, as MongoDB, we store documents in a JSON-like format. It's basically binary JSON. A bunch of these documents make up what we call the collection, and multiple collections are called a database again. In Cassandra, which is a white column store, it feels like it's a little. I needed at the time when I first ran into this, needed some time to really wrap my mind around it. So if you don't worry. You have basically these values, but they're like more stored vertically, and you have like column names on different, basically stored with the keys. So, and you can basically have some bunches. So basically, it looks like a relational table, like a little bit upside down, and is very efficient for query and also writing. For example, Cassandra is a database which is able to write faster than read, which is very unusual. And this is also like the Cassandra setup. So Cassandra consists of many, many nodes. They interact. So you can write to any node, which is different to other databases. So if you have like high-speed volume, Cassandra is a good choice for writing data. And there's the graph databases, and this what we call a graph. I think most of you are familiar with graphs. So we store nodes. The nodes could also have attributes, and then we have all these connections, and basically we could also like search a graph here. So from the data science perspective, of course, it's very important. How hard is it to collect data? Because it's very often a very time-consuming task. Some people say it's, okay, I need like 20%, 80% for data cleansing and 20% for the science. And so it's important to see, okay, how much effort is it to collect data? And of course, like with a relational database, we have to create a schema or work with a schema or extend the schema, especially from outside data with maybe unpredictable attributes. It might be very complex, but storing is easy. For MongoDB, since there is no schema enforced, that's pretty easy. The same with Cassandra. And Neo4j, I would also argue it's easy, but we can only store graphs in a graph database. So, well, I think that's, so we only can really prepare data to store it in a graph database. We cannot store anything there. So I'm put parentheses around it, yeah. You can have, like on the nodes, you can have attributes in Neo4j. So you can say this is the person, like a person node name and a gender and an email address, and you can extend it. So it's not only, okay, this is node 70 and it points to node 50 and 320. Yeah. So then what about data types? Because there's multiple data types in our data, and how can we deal with that? So of course, the relational database where we have data, it's enforced maybe, yeah? So like the schema defines this is the data type we want to store. Of course, there is also flexible formats, but in general, it's predefined. MongoDB, it's possible to enforce via schema control a data type, but the attributes are stored within the data type you send to the database. So you don't really have to worry. You basically can have one attribute and store a string and an integer there, if you have use for that. I would not do that, but it's basically not enforced. Cassandra, very similar. It's untyped collection columns where you can be flexible. So you have a schema predefined in Cassandra, because Cassandra, if you remember all these nodes and the power and the linear scalability of Cassandra, the more nodes we have in Cassandra, the faster we can read and write. Because it's a predefined schema, but it's also like an untyped collection columns data type, just like to mention it. So it's a little bit in between. And again, like with Neo4j, okay, we can only store graphs, so that's like a specialist here. So how hard is it to consolidate data? Yeah, okay, basically, it's basically pre-processing recommended because we can build a schema and link data. In MongoDB, we can pull the data in and basically do stuff within the database, and we also like flexible, and we can have post-processing jobs working on the database. So we can write a script, get this document, and see, okay, this is clean, or let's delete this because it's an outlier or dirty or whatever. So we can be flexible with post-processing here. And Cassandra, the linking is weird partitioning, so missing data, I would argue it's hard, because like the data is really torn apart in Cassandra, and also one of the storage concepts for performance, there's a lot of redundancy, and it's planned redundancies in Cassandra. So it can be challenging to pull all this together again. And for Neo4j, linking, of course, yes, I mean, it's a graph. Graph without links would be quite pointless. Missing data in a graph, I would say it's hard. Also find dirty data. But basically, all databases are really good in persisting a clean data set. I mean, it's a database, they store data so that any system is good at that. How hard is it to write queries? How hard is it to pull out data of these systems? I mean, it's nice we have these data store, but we need data. How will we query against these databases? And what can we basically do here? So Postgre uses SQL, as mentioned. It's a long and well-defined and well-common standard. It's for basic queries, it's easy, and I would argue for advanced queries, it can become hard because we have set theory involved, joins, left joins, right joins, outer joins, inner joins. So it can be tricky, but it's possible. So in MongoDB, it's MQL. That's different system basically. So MongoDB has a query language, which is it's very easy. Just you can pass in like an object with attribute and what you look for. You get a result. There's also an aggregation framework, which I'm going to cover in a bit, which is different to the SQL style. It's medium because you have to learn it. So Cassandra has CSQL, which is very close to SQL, and Neo4j has Cypher, which is also very close to SQL syntax. So summing that up, how querying, I mean, basic SQL, everybody should at least know basic SQL queries, like select and join some tables. This is an essential tool, and many systems build on that. Also, basically the philosophy of MongoDB, how to query, is also not alien from the SQL world. They only chose a little different approach for the aggregation, which I would say is a little bit human. So, how hard is querying to learn? SQL, basic query is easy. Hard, it can be hard, like unions and basically combining stuff. We'll see a few examples here. So like basically all the SQL are on the same, basically simple stuff is easy. If it's advanced, it can be really mind-bending, and due to the aggregation system MongoDB choose, I would argue it stays on the same level once you've learned it. So what are the SQL benefits here and the downsides? It's a common standard, it's long established. It's the mother of many other languages, querying languages. So it's always like a good ground to build on, even if you learn something else. It's set-based logic. The complexity can increase fast, and badly designed join can really drain performance. And if you make big joins with a lot of tables, it can be costly. If you do another join, you can get the same results and way faster, but you have to figure it out or basically have the expertise for that. It can be a lot of overhead understanding a large schema. So basically just like, okay, to understand what is the data stored in our database system, how can I access it, how is it interlinked. And also the set-based logic is on both sides, because some people have problems with like set-based, and depends on application maybe. So let's have a look at the queries. So we have, this is like a simple SQL statement. So this is what you should be able to do. And the next is more little bit, but it easily, and this is not a long one. I mean, like, remember, you have all many tables, you have to join, pull data and stuff, and it can easily look like this. And I think this is basically, we need to spend like 2 minutes or more to read it and to understand what's going on, what are we actually doing here. In Cassandra, which is also based on this is a simple Cassandra query, but we see, okay, it's very similar to the SQL syntax, and the more complex stuff gets, we will see something very similar like here. And Neo4j also is built on basically, it's very much like SQL. You have to know how to basically walk the graphs and to pull out the data you want to. A different approach is the MongoDB aggregation pipeline. So MongoDB chose a different way. So basically, we have a pipeline which is just like an array. And for example, so first the match is just like, okay, find data. This is basically a where clause in SQL. So we can find by some artist, and this is not a typo. And you can sort it by some other attribute. We can do a grouping and then a projection and just like pull data out. And for example, this is like really nice because if you just want to build your queries, we could just say, okay, match with the limit, match limit, only take like 10 documents and improve our aggregation pipeline. So basically, it's always like a step, and we only have to think about what are the data and how is the data organized from the previous step, and we can build on that. So we don't need to have these all sets and unions and joins. So basically, this is a straightforward process, and it looks a little bit like this, which I think is very abstract. But okay, we see like just follow the colors. So we do a match, and we only see the wet ones. If we do a projection, this is basically a renaming. And we basically do an addition between D and S, so we get something else, and then we can do a lookup, which is a join from another table. So we pull data from another collection here, actually, and do a sum. This is basically how it works. It's like a relay race. Right? If you're into like marathons, or you can pass on relays and everything. So okay, this is just like a quick match what you can do, where we want to go to. So, how hard is it to run? But from the data science perspective, from the I'm a trained database professional, and I'm doing this for like 10 years. So this is like, okay, if you just want to get a database running, how hard is it? How hard is it? I would say in a simple setup, it's easy for each and every of these systems. Then there's the aspect of maintenance. Do you have to do anything if the database is there for a while and has many, like maybe deletes, inserts, whatever? Yeah, but probably it's not that important from the data science perspective. But I would say it should be mostly a fixed data set. And then there's also like the question of how can I back up the whole system? And it can be a little bit more difficult with SQL databases. With no SQL, it's really nice because we can scale and replicate and just take one node. So if one server goes down, the other just continues. So basically, we run on multiple copies, and so it's quite easy to use one as a backup. Next question is, how hard is it to run analytics without affecting a production system? Because like, usually we want to go to a production system in a company. So PostgreSQL would say you have to replicate in a way in Medium, and there's also, you can also like basically say, okay, let's make an overnight copy if that's good enough for you. MongoDB, it's easy because you can have like hidden replica sets. So they get data from the production system, but they are hidden. So they will never become a primary, they will never accept writes. You can have basically a copy on your local computer if the computer is big enough. And and in Cassandra, it depends very much on the nodes and the partitioning of the whole system. So if it's like a huge Cassandra system, there's many, many nodes. There can be hundreds of thousands of them. In Neo4j, I would say, yeah, it's medium. It depends on the graph and how you work on a graph. Okay, let's get that. Okay, this is just like an example how horizontal and vertical scaling works. You can skip that. How hard is it to integrate into an existing system? It's basically fairly easy to medium, because if something's around, you can just like plug it in. And this is just like a type, so this is not something which you don't need to really worry about. How hard is it to change these systems, like from the authorization point? And this is all like, okay, they all have good roles and models, so you can run in a company and only limit the access to the data on role models. Okay. How hard is it to add new data? For the NoSQL systems, since they're not super defined and have a little bit more flexible, it's quite easy. On the relational database, it's like more easy medium. And if it's like already a complex structure, it can be hard because you need to update the schema. I also just like as a side note, PostgreSQL has also a NoSQL feature, so it even lets you store some attributes as a JSON. That's a nice feature of PostgreSQL, which I just want to mention. And of course, very important, how hard is it to understand the data structure? Small system, it's very easy. Medium, it can be harder, and if it's an extensive system, it can be very hard depending on where we are. And I'd really like, I'll just show you some examples. So this is basically a query to Cassandra, and this is what you get back. Because Cassandra has always like a primary ID, and then all the attributes are stored in a column, and you can have like a secondary index there, but then that's it. Basically, it's not really, you cannot have many indexes on one system here. But usually the technique is to tear it apart into different systems. I would say with a good visualization system, a graph is very readable. Of course, depending on the size and the density, but graph data you can visualize it really nicely and read and understand it. And as a comparison, the relational model is a lot depending on how many tables we have here. So this is like basically just like a simple address here, and we already have 5 tables involved, and this is how like we know it from a JSON or a dictionary in Python. So we see we have these sub-documents with an array, so basically this is just like one document, and we don't need to tear it apart in 5 tables. And so this is very readable. You can even give it like a web developer and say, hey, build a web shop or an address book. There's also some tools, for example, like MongoDB has Compass, where you can visualize and extract the data. There's also something built in Neo4j, where you can visualize and query and visualize your graphs. So these tools come out, and also like in the Neo4j. Did I say Cassandra? It's Neo4j. There's many tools for visualization for Neo4j. Growth, I don't think we need to worry about. So some more use cases except for storing data. You could also just easily use a database to store model parameters when you train an experiment, for example, a neural network. You can use it for documenting experiments because it's not some file on some computer. You can basically use a centralized system. So as a conclusion, I think there's not one solution really for which is the right database. There's not one database. You have to analyze what are your real needs in all dimensions. So complexity, knowledge, expertise, hardware, company rules. So I would really choose an accessible and simple solution, and don't try to reach too high, because many people ask me, oh, I have heard about this like specialized database. I said, yeah, well, does this database is there a community that can help you if you're a beginner? So I would really recommend, if you're new to the whole space, go to one of the top 30 systems, because you can get help, and otherwise you're pretty lost. And do not only focus on performance. Because usually people ask, oh, what's the performance of a database? Of course, it's very important. Fact is a very important measurement for performance and going fast, but it's not the main thing. I mean, you can have the most performant database, but if you're not able to interact with it, what's the point? I mean, it's like having a Ferrari without a driver's license. Play around, because they're open source. You have tutorials, and just go. So I would say a good choice for general purpose can be MongoDB, because the document is very readable, especially it's very close to Python dictionaries. If you work with graphs, go for Neo4j. If you have just like tables and you know already from university or other surroundings SQL, go for Postgres or like relational database system. And and if you're super new to the whole database space, I would say a document system can be very good because it's easy to understand and maintain. So, and you can read the rest of the slides. One more thing, this is a talk it's constantly updated, so if you're an expert in one of these systems and say, Alex, I totally disagree, tell me, let's discuss it and prove it. And I also want to thank Jens Dietrich already because I gave the talk 2 weeks ago and he gave me some really valuable feedback. And just follow me on LinkedIn, Twitter, and see updates. And thank you very much.
Thank you, Alexander.